Broadcasting from Boston, Massachusetts, the ARC Digital Transformation Viewpoints podcast is the only podcast dedicated to all things related to digital transformation in energy, industrial, and critical infrastructure applications. The podcast is the creation of the ARC Advisory Group Digital Transformation Practice. ARC advises leading companies on technology trends and market dynamics that affect their business. To engage further, please like and share our podcasts or reach out directly on Twitter at ARC_advisory, or please go to the website at www.arcweb.com.
Hello and welcome to this episode of ARC Advisory Group's Digital Transformation Podcast. I'm Harry Forbes from ARC Advisory Group, and today's podcast, we're going to discuss a new technology called Ethernet-APL for field devices and process plants. I'm going to be talking with Arnold Offner of Phoenix Contact. Arnold is Strategic Marketing Manager for Process Automation Infrastructure at Phoenix Contact. Phoenix Contact is a 100-year-old global firm originated in Germany and has moved from connectivity technology into many different forms of industrial automation infrastructure. Arnold, thank you for being here.
Thank you so much for inviting me, Harry.
Well, listen, Arnold, what we know about Ethernet-APL is that it's for the first time bringing IEEE standardized networking and extending it into the hazardous locations that we find in process plants. And there's roughly, or if you take an order of magnitude, 100 million field devices probably installed in the world, most of which are networked with 4 to 20 milliamp analog signals, maybe plus HART, and a small fraction with digital field bus, serial field bus technology, either foundation field bus or Profibus PA. Ethernet-APL is a change there, and bringing real, genuine, if you will, standardized, IEEE standardized networking into this space. Can you give me a little background on what you have done in that area and specifically what Phoenix Contact is contributing to this?
Thanks, Harry. So yes, Ethernet-APL could be considered an APL. The letters APL stand for Advanced Physical Layer. It essentially is a two-wire, I'll say, rendition of what we know to be Ethernet. Ethernet in its 8-wire configuration, 8-wire in a 4-pair configuration. And what the IEEE standards that you referred to developed is what we know as single-pair Ethernet, or SPE. And in looking at the SPE requirements, it became very clear that for the process automation space, the capability of going or remaining, 4 to 20 is a 2-wire system, field bus is a 2-wire system with power. It became very clear that a development of an advanced physical layer, which is nothing more than just layer 1, is actually going to be a good step forward for the process automation industry. And the standard that we refer to, of course, is the IEEE 802.3CG, which in its current form calls out for 1,000 meters at 10 megabits per second. So you can imagine that 10 megabits per second is now going to be a lot faster than what people are currently used to in their 4 to 20 milliamp networks.
Understand that. Now, it may sound slow by the IT standards of today, but it's certainly much faster than any of the legacy technologies that have been developed for field devices. So maybe you could explain just a little bit, since you have a lot of experience in the standards area, Arnold, what's the difference between the IEEE standard and the APL?
So the APL is really just an enhancement of that 2-wire or that single pair Ethernet standard known as T1L. So it's a long distance type connection. Essentially what we've done is we have then incorporated what we call 2Ys. So also standing for the acronym 2-wire intrinsically safe Ethernet. And what we've then also made sure is that we can actually make a very simplified intrinsically safe assembly that would allow us to simplify the installation of what we would call APL field devices or field instruments in the field, be able to run them 200 meters in an intrinsically safe manner into what we call zone 1, zone 0 areas. And then, of course, your APL field switch, which is what you're connecting to with this physical layer, is then either installed in a zone 2 environment, or there are probably manufacturers out there in future that would look at zone 1 installations as well.
In terms of interoperability, obviously Phoenix Contact is not the only company working in this area. There are automation suppliers, device manufacturers, and infrastructure suppliers like your company. So how is the standard and the groups that are working on this? Maybe you could explain who's working on this APL extension and what they're doing to guarantee the interoperability.
That's a very good question. So first we talk about the advanced physical layer as being developed in a group that was known as the APL project. That project was a consortium of the 4 leading standards development organizations. So we're talking about the FieldCom group, who we know from the HART and the Fieldbus days.
Yes.
Then, of course, we're talking about the ODVA, which is responsible for Ethernet IP. We're talking about the Profinet International Group, which is responsible for the Profinet profile, and of course Profibus PA of the past, as well as OPC-UA. So those are the 4 standards development organizations that then got together in a consortium with 12 manufacturers, Phoenix Contact being one of them. And what we then defined was essentially how we would create a physical layer so that we could actually go in 2 phases in our project. One, as a consortium, we would create a common physical layer, because that's the beauty of Ethernet. And then actually when the project itself was dissolved in August of 2022, what then happened was each of the relevant SDOs then went ahead with their work that was needed in actually deploying their particular industrial Ethernet protocol onto the physical layer. And that work is currently underway. So in other words, there is a NAMUR NE 168 recommendation that actually recommended the choice either of Ethernet IP or Profinet, because those are the 2 leading industrial Ethernet protocols in the marketplace today. So those being the, I'll say, industrial Ethernet protocols that then become the basis of what the NAMUR membership then looks to deploy at in the future.
What you're saying is that we're going to be deploying exclusively industrial Ethernet protocols on these networks. Is that correct?
That's the idea. Correct. In other words, if you look at how, shall we say, I think it's almost a 30% split right now, that almost represents 2/3 of the industrial Ethernet protocols in use today. And that's why Profinet and Ethernet IP was selected, also because they actually have very good market reach already in the space. And it's always good to have at least 2 leading technologies that then can be placed onto this very easily defined physical layer.
Okay, and that also gives, besides having an installed base, there's also an installed, an existing method and laboratories and all this for testing and guaranteeing interoperability.
Correct. And you also have a skilled enough workforce that has now been working on these technologies for the better part of almost 2 decades.
Is this just a question now? Where you mentioned OPC Foundation working on this,
Yes.
and FieldCom Group. So where is this going to expand? Are there going to be future protocols as well that are going to be added to this infrastructure?
So I think what we need to think about is you're looking at, firstly, having the PI and the FieldCom group together meant that you had the 2 leading SDOs that had already developed the Fieldbus technology, and really it is their customer base, their installed base of product and technology that can now migrate, at the Fieldbus speeds of 31 kilobits per second, 300 times faster to 10 megabits per second. If you then look at what the expertise is that each of these SDOs bring to the discussion, is that essentially what we then did was amongst the 3, what I'll call industrial protocol standards, the PI then got involved in actually catering and developing what we call the technical standard. The Fieldcom group was involved then in doing a lot of the testing. In other words, verifying that this idea of going to T1L at 200 meters in an intrinsically safe space would work. The idea being also to use existing field bus cables out of the IEC 61158, I think it is. So type A cable, currently in use, the idea was to actually keep that cable, installed cable, and make that, providing it tested out correctly and it hadn't aged, or it was and it was still performing at the limits that were required, it could now be that cable that could now support the physical layer. And then when you mention the ODVA, think about the ODVA then as being involved in what I would say was the marketing. So they led the marketing effort, which is what I was involved with. And then the OPC Foundation's contribution to this is quite significant, because I think we have to get ready for the idea that we're going to be looking at device information models. We're going to be looking at different, what I'll call digital device integration techniques. And that, I think, is where in future OPC UA then becomes also an interesting, what I will call not so much an industrial protocol as much as an industrial semantic platform to transfer data from an APL device through a switch back to a control system and then even onto the cloud.
Okay, so now you're getting into the topic here is how this technology with faster speeds and data rates and longer distances for standard networks can make some improvements and can make some changes in the existing environment, which has been around pretty much for a couple of decades.
Yes, I grew up with a 4 to 20 milliamp loop and a multimeter.
Me too. So, what do you see as the change or the major changes that this is going to bring?
I think this is finally us getting from what I would term is into the field device level with digital data. In other words, if you think about a 4 to 20 milliamp device, that field instrument is essentially taking data, converting it into a serial signal, which we then are basically sending in a 4 to 20 milliamp loop. And then, of course, we have a whole number of steps of analog to digital and digital to analog conversion taking place. What we now have with APL is the ability to put digital data right inside the field instrument and then send digital data. In other words, it doesn't have to be adapted or modified or converted again. We can actually send digital data directly from a field device to a switch. Now, realize that we're talking about 2-wire Ethernet or single pair Ethernet or APL from the field switch to the device. But what we're then doing is we're converting to our regular, what I will call IT type Ethernet-based networks all the way up into the automation pyramid. The beauty of this system now, of course, I think is also how some of these devices have become so complex. They have become a lot smarter. And so they actually have a lot more data in-house than just one, shall we say, variable. If you look at instruments like, for instance, a radar level detector, at AKIMA in June this year, Vega was showing very clearly how their comparison between a HART device, which of course is only running at about 1200 bits per second, was of course not reading a very highly fluctuating level inside a tank, and yet at 10 megabits per second, the accuracy, because the signal was so fast, was now closer to what was actually transpiring. And so I think what you're really looking at is this idea of Ethernet finally gets to the field device. We're talking digital data. We're also talking about faster speeds in transferring information to and from a field instrument or a field device. So one of the examples that I'm constantly also talking about is Coriolis flow meters. If you were to do that with HART, you're probably looking at 8 minutes. You do that in a field bus setting, you're probably looking at 3. And yet when you do it at 10 megabits per second, you're doing it in a matter of 3 to 4 seconds. In other words, data is now, of course, much faster for us. I always remember what dial-up speeds used to be like when I had my first Commodore 64. And times have changed now to where we take it for granted that these high speeds have to be there. And so I think this is actually how the process industry, both in the heavy and in the light industrial space, is now actually going to benefit from speed, because we're not waiting for a signal. We're actually getting that signal, as close to real time as we can get it.
Okay, and another question, we hear a lot about with, and this is been a question for a very long time in the process industries, is the stranded data as these devices have become much more intelligent. Basically, all the goings on within the device that don't pertain to the measurement have been largely invisible unless someone was actively looking at the device, with a specific diagnostic instrument.
Correct.
And how do you see that changing in the Ethernet APL? What is that going to do for different personas in a plant, the operator, the maintenance crews, and others?
So I think we're actually talking then about what I would say is the convergence of the IT side, because in the IT world, I think a lot of IT departments can check on, shall we say, the communication links to devices on a network. The same thing is now true in a process application. What I'll share with you too, I think, and this is the beauty of it, HART has unfortunately only always mostly been used either for fault finding or for setting up a device prior to its replacement in the field. It's never actually been HART live. In other words, being able to detect the HART data at any time when you needed to. And when you go from, when you're almost 10,000x the speed at which you can read data out of an instrument, what I see us now being able to do is, because it's all networked, we can now, without influencing the process, actually get data very quickly, very regularly, or as regularly as we want it, from an instrument that will tell us how long it's been in service, will tell us more about its future, shall we say, status. It could give us alarms and warnings that don't necessarily need to be detected in the control process, but probably a maintenance department want to look at. Your operational excellence folks might probably want to look at data to see just how well your valves are performing. So once APL valves become part of the APL infrastructure, I think there's going to be a tremendous benefit in that you now have the access to information at any one time. And I think that's clear in a networked environment. And of course, the biggest challenge now is, of course, making sure that the OT folks, the operational technology folks, it's their job to make sure that the process is always running. And so you have to make APL as simple as possible. In other words, you can't make it more complicated than swapping out a 4 to 20 milliamp device, which is one of the things that the Nomura NE168 recommendation calls for. There is, in fact, another Nomura recommendation or another Nomura project at hand, which is known as the Nomura Open Architecture. And I think what this allows us to do is to actually use what they're terming as a side channel, which allows you to extract data out of your process without conflicting or without compromising your process itself, but actually having access to data points that other people in the organization on campus might want to see or might want to compare and, shall we say, assess. It's a great way now of not having to send somebody into the field to go and check something with a screwdriver. It's easier just to do it from the comfort of your air-conditioned office on a PC.
Well, I can see that what you're saying, and what I'm taking from that is that we're going to be in the future monitoring process field devices much the same way we monitor IT devices now. And that means continuously and in great detail.
Yes.
Which is something we've never been able to do.
No, you're right.
Arnold, just to kind of wrap up, I'd like to continue this maybe at another time. Maybe we can have this discussion again or continue this discussion. But maybe you could, to wrap up, kind of give us a view of when these things are going to roll out, the infrastructure that you all and others are building, and the field devices, and when are these products going to be rolling out?
Yes. So there are very intensive efforts right now to, shall we say, make sure that we have an ecosystem that expands to include the controllers, the infrastructure switches that you're referring to, where Phoenix Contact is involved, in the APL field devices. I would currently say that right now we are in the process of launching the first systems that will be, shall we say, incorporating a DCS, a distributed control system that can basically process the APL data. Phoenix Contact launched their first 24-port switch, field switch, at the AKIMA back in June in Frankfurt, Germany. So that's the world's largest process trade show. We have other infrastructure suppliers as well that have already launched product 2, and there are more products on the horizon. I think later this year is when the current market survey says they will be ready as well. And then I think what you need to realize too is that these field instruments, they also need to then be, shall we say, adapted, designed to cater for APL. And so you're looking at things like a very comprehensive range of different products depending on the, like I say, the original 12 APL project team members, but you're looking at things like temperature, you're looking at things like pressure, you're looking at things like flow, control valves. And so all these products now come to market. The beauty of it, I think, being we've now created a true digital connection to those products. And so I'd say stay tuned, because I think in the coming years, maybe in the next year or so, we'll start to hear about the first deployments of APL, all the way from DCS through field switch, all the way to field instrument. And I think the other thing I'll mention too, and I think this is actually going to be liberating for the users of the field devices themselves. APL really allows the field device to unleash the true potential of APL. So a field device does no longer need to be, shall we say, connected to a controller so that the controller can determine things like, well, how much flow rate did I have from Monday until Friday. That totalizing data can actually be running inside the device. So it frees up your control system too. And so as we were talking about APL and talking about all this additional functionality, I would say that the clear message is that the APL field instrument finally gets its access to the network, because it's the field device that's really going to be the star of the show. You know, working 10,000 times faster than HART, working 300 times faster than a regular field bus device. But there's all this additional, I'd say, latent competency inside the field instrument that really takes us to a whole new level. And if we do get to do a second podcast, I'm thinking it'd be a great idea to also demonstrate to you just some of the benefits and features that do come with an APL switch.
Oh, that'd be great, Arnold. I really look forward to it. And maybe we should schedule that pretty soon.
Yes, we should.
Okay, well, thanks a lot for your time, Arnold. It's really been great talking with you, and look forward to doing this again.
Thank you so much, Harry. And thanks to our listeners out there.
This is Harry Forbes of ARC Advisory Group. I've been talking with Arnold Offner of Phoenix Contact about Ethernet-APL as part of our ARC Advisory Group's Digital Transformation podcast. Thank you all for listening.